In this video, we're going to go over finding inverses for secant, cosecant, and cotangent functions. And these are three functions I didn't address in the first three videos I did. We did sine, cosine, tangent. We could go through and come up with inverse functions for each of these three functions using kind of the same techniques that we did for sine, cosine, and tangent. So I'm not going to do that for these functions other than to establish that they indeed do have inverses. And you actually should be able to look at the graphs of the secant, cosecant, and cotangent functions and kind of come up with what would the restricted domains need to be. And that should be something that could actually be left as an exercise. But let's just talk through these three real quickly without being too detailed. And then we want to go over how do you find an inverse value for one of these functions if you need to, given that our calculators don't typically have keys that have those functions on them. Usually your graphing calculator, like the Texas Instruments, it's going to have inverse tangent, inverse sine, inverse cosine, and that's it. So the secant function does have an inverse. It's going to be named the same way that we were naming inverses before. So it's going to have an inverse called the arc secant. Or you can write it as secant inverse, this type of notation. We know that the secant function takes angles as its inputs and outputs the reciprocal of the cosine function. So the cosine function, you input theta, the output is the x-coordinate on the unit circle. For the secant function, the output would be 1 over x, 1 over the x-coordinate on the unit circle. So the input for the arc secant function, which we shorten like this, is going to be the side ratio 1 over x, the reciprocal of what you would be putting into the cosine function, or we could say secant inverse of 1 over x. The cosecant function has an inverse arc cosecant, and inverse notation you would say cosecant inverse. So if we have the cosecant function, we know that we input theta, and the output's going to be a 1 over y, 1 over the y coordinate on the unit circle. So the arc cosecant, the inputs would be 1 over the y coordinate associated with this angle on the unit circle, or we could say cosecant inverse of 1 over the y coordinate associated with the angle on the unit circle. And the same stuff for cotangent. We've got a cotangent function. So there is indeed an arc cotangent function, an inverse function for cotangent. Cotangent. We could use the inverse notation. We know that the cotangent function takes an angle as an input, and the output is y over x. So we get the arc tangent function. The input would be the ratio y over x, or we could say tangent inverse. The input would be the ratio y over x. If you weren't on the unit circle, the only thing that would change here is you would say, well, the secant of theta outputs the radius over x. Remember, we had defined r to be the square root of x squared plus y squared if we're on a circle that isn't radius 1. So the only thing that would change in any of these would be, if we're not on the unit circle, this is going to be that radius r. The definition won't change for tangent because y over x is y over x. So and these all have restricted domains, restricted ranges. And it's something that is something you can look up on your own. We did it concretely for sine, cosine, tangent. That's what it's most important to do it for. The others can be looked up easily, or you could even look at the graphs of the functions and figure it out on your own. The problem is if you are actually working with something where you have the secant of some angle theta equaling stuff. So here's where you run into a problem. And what you want to know is what the angle theta is. So the typical approach would be to say, hey, I'm going to take the arc secant of both sides. In other words, you apply the inverse function. So you get arc secant of stuff. And this will output theta. The arc secant, you input a side ratio, it outputs the angle theta as long as the angle is in the range of the inverse function, the arc secant. So you get theta equals the arc secant of stuff. And the problem is if you need to approximate this, your calculator doesn't have a key for doing the arc secant. If you have a computer algebra system, it may well just allow you to do arc secant as a function and do it for you, but our typical graphing calculator can't handle this. So the way that you deal with this is you just use the fact that the secant function, if you have secant of theta equaling stuff, we just want to remember that the secant is by definition 1 over the cosine. This is our reciprocal identity, which means that you could multiply both sides by the cosine. I'm going to do a little more algebra than what I think is necessary just to make sure I don't lose anyone. And then we could divide both sides by the stuff. So we get 1 over stuff equaling the cosine. And hey, I can take the cosine inverse of both sides. So here I could do the cosine inverse of 1 over the stuff. And this would be equal to the cosine inverse of the cosine of theta. And as long as theta is in the range of the cosine inverse function, pop, out comes theta, and I get the cosine inverse of 1 over stuff equals theta. So I can get theta either one of these two ways, which means that the secant inverse, or the arc secant of stuff, is equivalent to the cosine inverse of 1 over stuff, as long as the stuff wasn't equal to something silly like 0, which it can't be because of the range of the secant function, so we don't need to worry about that. So we get these two statements that are equivalent, and this makes sense. If the thing that you're supposed to put into the secant inverse function is the side ratio r over x, well, we know that what you put into the inverse secant function has to be the reciprocal of what's going into the cosine inverse function, because the secant and the cosine have the inverse relationship. So that's how you deal with it. If you need to know secant theta of stuff, if you need to solve this for theta, just do a quick switch here and say, hey, if I have the secant of theta equals stuff, that means that the cosine of theta, because it's the reciprocal of the secant function, is just going to equal 1 over the stuff, and take the cosine inverse of both sides, so you get cosine inverse of 1 over stuff equals theta. And the technique that you would use for dealing with arc cosecant and arc tangent is basically the same. You would want to realize, if you're working with the cosecant function, if you had cosecant of theta equaling stuff, just recognize that means that the sine of theta equals the reciprocal of that. Use the inverse sine function to solve it. If you're working with the cotangent function, we have cotangent of theta equals stuff. I got horrible penmanship going on here. Just remember that the cotangent is the reciprocal of the tangent. Do tangent theta 1 over stuff. And in each of these cases, the only restriction we would have is that stuff couldn't be 0. And as long as that's not the case, we can convert everything over into sine, cosine, or tangent world and deal with it using the inverse sine, inverse tangent, inverse cosine functions that we've already well established.